Welcome back guys. In this video we are going to complete Cryptography Basics room from TryHackMe. In this room we are going to learn the basics of cryptography and symmetric encryption. Let's move to the task number 1, Introduction. Have you ever wondered how to prevent third parties from reading your messages? How can your app or web browser build a secure channel with a remote server? By secure we mean that no one can read or alter the exchanged data. Furthermore, we can be confident that we are connecting with the real server. Thanks to the cryptography, these requirements are satisfied. Cryptography lays the foundation for our digital world. While networking protocols have made it possible for devices spread across the globe to communicate, cryptography has made it possible to trust this communication. Okay. Learning objectives. Upon completing this room, you will learn the following: cryptography, key terms, importance of cryptography, Caesar cipher, standard symmetric ciphers, common asymmetric ciphers, and basic mathematics commonly used in cryptography. Okay, now let's move to the task number 2, importance of cryptography. Cryptography's ultimate purpose is to ensure secure communication in the presence of adversaries. The term secure includes confidentiality and integrity of the communicated data. Cryptography can be defined as the practice and study of techniques for secure communication and data protection, where we expect the presence of adversaries and third parties. In other words, these adversaries should not be able to disclose or alter the contents of the messages. True. Okay. Cryptography is used to protect confidentiality, integrity, and authenticity. In this age, you use cryptography daily. You almost certainly reading this over an encrypted connection. Consider the following scenarios where you would use cryptography. When you log on to TryHackMe, your credentials are encrypted and sent to server so that no one can retrieve them by snooping on your connection. When you connect over SSH, your SSH client and the server establish an encrypted tunnel so no one can eavesdrop on your session. When you conduct online banking, your browser checks the remote server certificate to confirm that you are communicating with your bank's server and not an attacker's. When you download a file, how do you check if it was downloaded correctly? Cryptography provides a solution through hash functions to confirm that your file is identical to the original one. As you can see, you rarely have to interact directly with cryptography, but its solution and implications are everywhere in the digital world. Consider the case where a company wants to handle credit card information and process related transactions. When handling credit cards, the company must follow and enforce the Payment Card Industry Data Security Standard (PCI DSS). In this case, the PCI DSS ensures a minimum level of security to store, process, and transmit data related to credit cards. If you check the PCI DSS for large organizations, you will learn that the data should be encrypted both while being stored and while being transmitted. In the same way that handling payment cards details require compiling with PCI DSS, handling medical records require complying with their respective standards. Unlike credit cards, the standards for handling medical records vary from one country to another. Example laws and regulations that should be considered when handling medical records include HIPAA, Health Insurance Portability and Accountability Act, and HITECH, Health Information Technology for Economic and Clinical Health in the USA, and GDPR, General Data Protection Regulation in the EU, and DPA, Data Protection Act in the UK. Although the list is not exhaustive, it gives an idea about legal requirements that healthcare providers should consider depending on their country. These laws and regulations show that cryptography is necessary, that should be present yet usually hidden from the direct user access. Okay, now let's answer the questions. What is the standard required for handling credit card information? It is PCI-DSS. Now let's move to the task 3, plain text to ciphertext. Let's start with an illustration before introducing the key terms. We begin with the plain text that we want to encrypt. The plain text is the readable data. It can be anything from a simple hello, a cat photo, credit card information, or medical health records. From a cryptography perspective, these are all plain text messages waiting to be encrypted. The plain text is passed through the encryption function along with a proper key. The encryption function returns a ciphertext. The encryption function is the part of cipher. A cipher is an algorithm to convert a plain text into ciphertext, and also vice versa. Now to recover the plain text, we must pass the ciphertext along with the proper key via the decryption function, which should give us the original plain text. This is shown in the illustration. So when we encrypt, we use key, and then we also use the same key to decrypt to plain text. We just have introduced several new terms, and we need to learn them to understand any text about cryptography. The terms are listed below. Plain text is the original readable message or data before it's encrypted. It can be a document, image, multimedia file, or any other binary data. Ciphertext is the scrambled, unreadable version of the message after encryption. Ideally, we cannot get any information about the plain text except its approximate size. Cipher is an algorithm or method to convert plain text into ciphertext and back again. A cipher is usually developed by a mathematician. Next, key. Key is a string of bits the cipher uses to encrypt or decrypt data. In general, the used cipher is public knowledge. However, the key must remain secret unless it is public key in asymmetric encryption. We will visit asymmetric encryption in the later task. Encryption. Encryption is the process of converting plain text into ciphertext using a cipher and a key. Unlike the key, the choice of the cipher is disclosed. Decryption is the reverse process of encryption, converting ciphertext back into plain text using a cipher and a key. Although the cipher would be public knowledge, recovering the plain text without knowledge of the key should be impossible. That is infeasible. Okay, let's answer the questions. What do you call the encrypted plain text? The plain text which is encrypted is called as ciphertext. What do you call the process that returns the plain text? It is decryption. Now let's move to the task number 4. Historical ciphers. Cryptography's history is long and dates back to the ancient Egypt in 1900 BCE. However, one of the simplest historical ciphers is the Caesar cipher from the 1st century BCE. The idea is simple: shift each letter by a certain number to encrypt the message. Consider the following example. If we take the plain text as try hack me and key would be 3, assume it is right shift of 3, and the cipher is Caesar cipher. We can easily figure out that T becomes W because we have to shift right from the T, and the key is 3, so we have to shift 3 characters right from T, and R becomes U, and so on. As you noticed, once we reach Z, we start all over as shown in the figure below. Consequently, we get the ciphertext for the try hack me. To decrypt, we need the following information: the ciphertext, the key to decrypt, and the cipher that we are going to use. For encryption, we shift to the right by 3, and for decryption, we shift to the left by 3 and recover the original plain text, as illustrated in the image above. However, if someone gives you a ciphertext and tells you that it was encrypted using Caesar cipher, recovering the original text would be a trivial task, as there are only 25 possible keys. The English alphabet is 26 letters, and shifting by 26 will keep the letters unchanged. Hence, 25 valid keys for encryption with Caesar cipher. The figure below shows how decryption will succeed by attempting all the possible keys. In this case, we recover the original message key with the key 5. Consequently, by today's standards, where the cipher is publicly known, Caesar cipher is considered insecure. So we can brute force with keys from 1 to 25, and then for any one of the key we would get the answer if the plaintext is encrypted in Caesar cipher. You would come across many more historical ciphers in movies, cryptography books. For example, the Vigenère cipher from the 16th century, the Enigma machine from World War II, the one-time pad from the Cold War. Let's answer the questions. Knowing that the text was encrypted using Caesar cipher, what is the original plaintext? Okay, now for this cipher text we should brute force the Caesar cipher from keys 1 to 25. So to do this we have many online tools. One such tool is decode.fr. So inside this, if we go and paste the cipher text, and then when we run the decrypt of brute force, we can see the results of all the keys applied here and all the plain text that is outputted in here. So decode.fr tool is smart enough to recognize the English words, so it has given the correct output at the first row. The key here is 15 to the right. Let's copy this. Now let's move on to the task number 5, types of encryption. There are two main categories of encryptions, symmetric and asymmetric. Symmetric encryption, also known as symmetric cryptography, uses the same key to encrypt and decrypt the data as shown in the figure below. Keeping the key secret is a must. It is also called private key cryptography. Furthermore, communicating the key to the intended parties can be challenging as it requires a secure communication channel. Maintaining the secrecy of the key can be a significant challenge, especially if there are many recipients. The problem becomes more severe in the presence of powerful adversary. Consider the threat of industrial espionage, for instance. So in the symmetric encryption, there is only one key used to encrypt or decrypt, which is similar to Caesar cipher. Consider the simple case where you created a password protected document to share it with your colleague. You can easily email the encrypted document to your colleague, but most likely you cannot email them the password. The reason is that anyone with access to their mailbox would access both the password protected document and its password. Therefore, you need to think of a different way, that is a different channel to share the password. Unless you think of secure accessible channel, one solution would be to meet in person and communicate the password to them. Examples of symmetric encryption are DES, Data Encryption Standard, 3DES, Triple DES, and AES, Advanced Encryption Standard. DES was adopted as a standard in 1977 and uses a 56-bit key. With the advancement in computing power, in 1999 a DES key was successfully broken in less than 24 hours, motivating the shift to 3DES. 3DES is a DES applied 3 times. Consequently, the key size is 168 bits, though the effective security is still 112 bits. 3DES is more of an ad hoc solution when DES was no longer considered secure. 3DES was deprecated in 2019 and should be replaced by AES. However, it may still found in some legacy systems. AES was adopted as a standard in 2001. Its key size can be 128, 192 or 256 bits. There are many more symmetric encryption ciphers used in various applications. However, they have not been adopted as standards. Next, asymmetric encryption. Unlike symmetric encryption, which uses the same key for encryption and decryption, asymmetric encryption uses a pair of keys, one to encrypt and one to decrypt. As shown in the illustration below, to protect confidentiality, asymmetric encryption or asymmetric cryptography encrypts the data using public key, hence it is also called public key cryptography. So if we observe this image, when Alice wants to send a message to Bob, Alice will encrypt the message using Bob's public key. Now when Bob receives the ciphertext, Bob will decrypt his message using his own private key. Since Alice used Bob's public key, the text can be also decrypted with Bob's private key. This is a basic example for asymmetric encryption. Examples are RSA, Diffie-Hellman and elliptic curve cryptography. The two keys involved in the process are referred to as public key and a private key. Data encrypted with the public key can be decrypted with a private key. Your private key needs to be kept private, hence the name. Asymmetric encryption tends to be slower, and many asymmetric encryption ciphers use larger keys than symmetric encryption. For example, RSA uses 2048-bit, 3072-bit and 4096-bit keys. 2048-bit is the recommended minimum key size. Diffie-Hellman also has a recommended minimum key size of 2048, but uses 3072-bit and 4096-bit keys for enhanced security. On the other hand, ECC can achieve equivalent security with shorter keys. For example, with a 256-bit key, ECC provides a level of security comparable to a 3072-bit RSA key. Okay, asymmetric encryption is based on a particular group of mathematical problems that are easy to compute in one direction, but extremely difficult to do the reverse. In this context, extremely difficult means practically infeasible. For example, we can rely on mathematical problem that would take a very long time, for example million of years, to solve using today's technology. We will visit various asymmetric encryption ciphers in the next room. For now, the most important thing to note is that asymmetric encryption provides you with a public key that you can share with everyone and a private key that you keep guarded and secret. Now let's answer the questions. Should you trust DES? No, because DES was already brute forced within 24 hours. Can be brute forced within 24 hours. When was AES adopted as an encryption standard? AES was adopted in 2001. Okay, now let's move to the task 6, basic math. The building blocks of modern cryptography lies in mathematics. To demonstrate some basic algorithms, we will cover two mathematical operations that are used in various algorithms: XOR operation and modulo operation. XOR, short for exclusive OR, is a logical operation in binary arithmetic that plays a crucial role in various computing and cryptographic applications. In binary, XOR compares two bits and returns 1 if the bits are different and 0 if they are same, as shown in the truth table below. This operation is often represented by the symbol plus with circle or a cap. If this is the first time you work with a truth table, it is a table that shows all possible outcomes. The XOR truth table above states all four cases. That is, when A and B are 0 0, the result would be 0. If they are 0 1, the result would be 1. If they are 1 0, the result would be 1, and if they are 1 1, the result would be 0. So if the state of A and B are same, then the result will be 0 every time. Let's consider an example where we want to apply XOR to the binary numbers 1010 and 1100. In this case, we perform the operation by bit. that is first bit of the first number with first bit of second number and so on, which will result in 0110. You may be wondering how XOR can play any role in cryptography. XOR has several interesting properties that make it useful in cryptography and error detection. One key property is that applying XOR to a value with itself results in 0, and applying XOR to any value with 0 leaves it unchanged. That means A XOR A is 0 and A XOR 0 is A for any binary value A. Additionally, XOR is also commutative, that is A XOR B will be equal to B XOR A, and it is also associative, that is A XOR B then XOR C will also be equal to B XOR C, and then A XOR the result. Let's see how we can make use of the above in cryptography. We will demonstrate how XOR can be used as a basic symmetric encryption algorithm. Consider the binary values P and K, where P is the plaintext and K is the secret key. The cipher will be P XOR K. So let's take this equation, C equals to P XOR K. Now if we XOR K on both sides, then we would get this equation, C XOR K equals to P XOR K whole XOR K. Now we know that XOR satisfies associative property. That means we can write the right hand side as P XOR of K XOR K. So we also know that K XOR K will be equal to 0. Then that becomes P XOR 0, and then we know P XOR 0 is P. That means the whole right hand side will become P. That means we would get the equation P equals to C XOR K. That means the plain text will be ciphertext XOR with K, that is the key. Therefore, as long as we have the key and ciphertext, we would get the plain text using XOR operation. That provided the ciphertext is also an operation of XOR. Let's move on to the next, modulo operation. Another mathematical operation we often encounter in cryptography is the modulo operator, commonly written as percentage or as mod. The modulo operator x percentage y is the remainder when x is divided by y. In our daily life calculations, we focus more on the result of division than on the remainder. The remainder plays a significant role in cryptography. You need to work with large numbers when solving some cryptography exercises. If your calculator fails, we suggest using programming languages such as Python. Python has a built-in int type that can handle integers of arbitrary size and would automatically switch to larger types as needed. Many other programming languages have dedicated libraries for big integers. If you prefer to do your math online, you can also use Wolfram Alpha. Let's see some of the examples for modulo operations. So 25 mod 5 will result in 0 because 25 divided by 5 is 5 and the remainder is 0. Then 23 mod 6, the result will be 5 because when 23 is divided by 6, we will get the remainder of 5. And similarly 23 mod 7, we get the result 2 because when we divide 23 with 7, we will get the remainder 2. An important thing to remember about modulo is that it's not reversible. If we are given the equation x mod 5 equals to 4, there are infinite values of x that would satisfy this equation. That is, if one number is divided by 5, then the remainder will be 4. So for example, if we take x as 14, then if 14 is divided by 5, then 5 times 2 will be 10 and we will get a remainder of 4. Similarly, if we take 19 as x, then we will get 5 times 3 15 and we will get the remainder 4. Therefore x will have infinite values. The modulo operator always returns a non-negative result less than the divisor. This means that for any integer a and positive integer n, the results of a mod n will always be in the range of 0 to n minus 1. Okay, now let's answer these questions. So these are basic math questions. We can either use Wolfram Alpha or programming languages such as Python. In this case, I will use Python as it is easy and we can run them in local. Okay, the first question is 1001 XOR with 1010. So these are binary numbers. First we have to convert binary numbers to integers. So if we see that 1010 is 1 plus 8, that is the first number is 9 XOR, and 1010 that is 2 plus 8, it is 10. Now we get the 9 XOR 10 result is 3. So we have to convert the 3 to back to binary. So 0011 will be the representation of 3 in binary. Now let's move to the next question. Okay, it is a modulo operation. 118613 modulo 9091. So this results in 3565. Cool. Now let's move to the next question. We can directly see here 60 mod 12. 12 times 5 is 60. That means the remainder will be 0. Let's test that. Yeah, so the answer is 0. Let's move to the task number 7, summary. In this room we learned about the importance of cryptography and some of the problems that it solves. We also introduced symmetric and asymmetric encryption ciphers. Finally, we explained the XOR and modulo operations. In the next room, public key cryptography basics, we will visit various asymmetric crypto systems and see how they solve the problems we face in the digital world. Cool. Let's complete this. Okay. Thank you guys for watching this walkthrough. If you like this type of videos, also watch my other walkthroughs of Try Hack Me rooms.